hopefully that's all the technical issues. So hi, my name is Jack Koenig, as it says up there. I work at Sci5 and I work on Chisel, as you can tell by my felon orange shirt. I don't know why we picked this color for the first conference. We never picked it again. So OG shirt here, but I'm going to tell you about Chisel 6 and what we've been working on, and some of you who have not seen a talk from me in the last year are wondering what happened to Chisel 3. I'll talk about that in a minute. All right, so the outline of what I'm going to talk about is I'll give some background because there's always, hopefully, at least one or two people in the room who have no idea what I'm talking about, and maybe people watching online in the future. And then I'm going to dive into more of the details that are mostly relevant to people who use Chisel, but hopefully it'll be interesting to the rest of you as well. So what is Chisel? It's an acronym constructing hardware in a Scala embedded language. It's a domain-specific language where that domain is digital design, like Verilog, like a lot of the stuff we're talking about here. It is neither HLS nor behavioral synthesis. We are not converting Scala to gates. We are running a program. The execution of that program constructs a hardware design and then emits Verilog at the end. You write this program, you can use things like parameterized types, object-oriented programming, functional programming, and static typing, which for people who are interested in programming languages, we think are good things. And it's intended for writing reusable hardware generators, which you might think of as a library, something that you write once and then can use lots of times. So as I mentioned, it is not high-level synthesis or anything. You can write something very Verilog-like. So this is a moving sum filter, if you will, or just moving sum. It has an input. It has two registers. We have Z1, Z2, and then we add up the current input value with the two previous values to get the output, right? That looks, yes, it's obviously syntactically different than Verilog, but the basic gist of I have registers and I have logic is exactly the same. But the question is, okay, a moving sum, isn't that useful? What if I want more than 3 points? What if I want weighted averages? What I really want is a generic FIR filter. And so this is probably a little bit small, and I'm not really here for a coding lecture, so I'll just gloss over some of the details. But the idea here is that you can parameterize not only the bit width, which of course you can do in Verilog as well, but you can also parameterize the magnitude and number of the coefficients. And so just by this single generator now, you can have arbitrary numbers of cycles that you're filtering over and different weights that you can apply. And yet this has no, this does not sacrifice any expressibility or performance. If you were to plug in 1 and 1 as coefficients, you would get the exact same adder, or the exact same filter as before. And so that's what you can see here. You get the exact same one, exact same Verilog. You can get a delay filter, a triangle filter, whatever. Okay, so now that you're all Chisel experts, we're going to dive into the details of development. So one of the biggest change that has happened kind of over the last couple of years is we have a new FIRRTL compiler. So FIRRTL is the intermediate representation, IR, underneath Chisel. And the original one was written in Scala, and it has been rewritten using MLIR, which is, for those who don't know, it's a multi-level intermediate representation. It's a generalization of LLVM to make it support arbitrary compilers, basically. It's much faster and uses less memory. That's great, but the main goal was really just we wanted more rapid feature development. LLVM is all about productively writing compilers, and this is a compiler, so now by using MLIR, we can much more rapidly develop. This did result in some legacy and lesser used APIs being removed when we went from Chisel 3 to Chisel 5. But some of these were things that nobody really wanted, like import capital C Chisel. Some of them are things that people do like that we hope can be rewritten as libraries. The one real big unfortunate thing was by the loss of the Scala FIRRTL compiler, then anything using it is kind of, is harmed by that. Chisel test is a great library that people use. And Kevin, who's here, has done some great work continuing it, working with some of the newer versions of Chisel. But in order to work with FIRRTL, which is the MLIR FIRRTL compiler, we have this new thing, what we call Chisel Sim, that isn't to feature parity with Chisel tests yet, but the hope is eventually it can implement all of those features. But one also important thing is the smaller public API surface of the new FIRRTL compiler makes it much easier to develop. It was harder when you have tons of APIs to maintain. It makes it harder to change things as you move forward. Right. So this change we decided to reflect by changing the versioning scheme. So instead of Chisel 3 and always having a 3 as the first version number, we've moved to Symver. So we've released Chisel 5, Chisel 6. I'm working on releasing Chisel 7. And we monorepoized just to make the release process a lot easier. I released 2 minor versions while I was sitting here, because it's all automated now, whereas it used to take me all day to get a release out. So what's new as of 7.0.0 milestone 2, which that artifact does not exist. There's 1 or 2 things I'm trying to get merged before I tag that one. But this is basically the head of main, if you will. So for anyone who tried out Chisel with FIRRTL maybe a year ago, one of the biggest annoyances is it used to be really easy to install because it's just one, it all works in the same, I don't know, sandbox, if you will. It's all Scala. But now FIRRTL will automatically be downloaded by Chisel, so it makes it much easier to run it. This is true as of Chisel 6, not on the Chisel 5 line, unfortunately. I'm trying to get that backported. And it supports Linux, Mac, Windows, except for Linux, ARM64. If anybody wants to help with that, that'd be great. But those are the things that are currently working. We have a new website, so I'm very excited about this. If you haven't used Docusaurus for your website generator, it's pretty good. I strongly recommend checking it out. I'm very happy with it. We have search powered by Algolia. It has dark mode. And then along with this new website, we wrote this new installation page to make it easier to try Chisel. So if you're curious, just go to chiselllang.org and click on the Getting Started link, and it will take you to this. And it's pretty easy to generate Verilog. It should only one thing you have to install, and then it should just work. TM. All right, moving on. So now I'm going to talk more about specific features. So one of the big ones is intrinsics. So in the past, you could extend functionality of the Scala FIRRTL compiler by using annotations and transformations, and that was kind of difficult to do. But most importantly, it's super duper flexible, perhaps too flexible. And intrinsics are a bit more restricted, but therefore composable. And so it's allowed us to add a lot of features that we're not exactly sure if they should be FIRRTL spec yet or not, but they let us do things a lot faster. Some examples are things like clock gates, dealing with plus args. We don't really deal with X, so if you need to for some reason, you can query some things in X. But one of the coolest things that have been implemented with intrinsics are linear temporal properties, also known as SVA, system Verilog assertions. Something that people have asked for a really long time. We have it, it works. You can see the Chisel example of a couple things on the top, and then this is the actual Verilog that it emits. Now you may note this is a lot of Verilog. Why isn't it just these 2 properties? One of the things we found in interacting with verification engineers is that the behavior you want for the vast majority of your assertions is you want it to only be valid after you've reset the thing, right? One of the biggest annoyances with setting up assertions is dealing with the fact that they're always firing as soon as simulation starts, and you have to do all this stuff. So we decided to pick sensible defaults, and your resets, by default, your properties don't start checking until reset has been asserted and deasserted. And so that's really handy as a default. It's only the default. You can always add resets. People need assertions during reset too. You can do that. That's just not the default. The default is this nice behavior. And it's been, at least the verification engineers I work with are loving it. So it's working really well. Another thing is probes, which are also known as reference types or maybe XMRs. You need a way of talking about things that are not ports on your design. But in Verilog, with Verilog XMRs, that means every single signal in your design is part of your public API, right? It's like somebody's going to dot into it, and now you change it, and they're like, why did you break my verification stuff? And you're like, I just changed something. So probes are our way of creating, so I have a couple probes here. It doesn't really matter that much, but we emit these define files so that this name right here, like ref foo io probe, which kind of comes from where the probe is defined in the public API, that name is stable and will never change. And you can change the internals of your design, and that link will still work. So you don't dot into the Verilog, you just use this define, and it will continue working by Verilog API. And then that goes along with this other feature. So many of you are probably familiar with bind in system Verilog, and bind is great, but it has some important limitations. For example, the spec doesn't let you bind into something you're binding in. Now, VCS and Verilator support that, but other tools don't. So that's one thing. You can't, if you have things you're binding in, you can't communicate between them very easily. That's really difficult to do. So we have this concept called layers, which is sort of a way of describing logic that is non-functional, basically read verification. And it will be extracted out into files that are bound in, but you can communicate across them. So and you can compose them and nest them, and we generate the right sets of defines and bindings and cross-module references to make it work. So it's kind of like system Verilog bind with a lot of extra features. And this is really powerful for adding verification logic without having it impact the design. Properties are another important thing because we have our design, we verify it, but what about the rest of the world, like your software, all the types of collateral you need to generate. So this part is still very much under active development, but it's essentially a way to describe like non-hardware values that are related to the design. So address maps are a really good example. Like you have a base address, and then you can calculate all the addresses from that directly in Chisel. And then you can use there's a Python library to query to essentially like evaluate if I give you this input, what is the output? What output properties do I get? That's still under development. And this one is very hard to see, but it's extremely exciting. So wow, that is really low resolution. But some of you may know that that looks kind of like Verdi, and it is. And if you can hopefully tell, this looks kind of like Chisel, and it is. And this is production Verdi, now supports source level debugging of Chisel, which is pretty exciting. It's an alpha level feature, so it works. I don't know how well, I haven't stress tested it, but this is actual waveform debugging of Chisel directly in Verdi. Now, this is an open source hardware conference, and of course we are open source, try to be good open source stewards, so this format that is used for this is open source. It's part of Circuit, HGLDD, the Hardware Generator Language Debug Data. It was built in collaboration with Synopsys, but it's not specific to Chisel, and it's not specific to Synopsys, so anyone else can implement it in their waveform viewer, and anyone else can generate it, and you can get source level debugging just like we have. And so that means that people in the open source community have already found it. So this is also extremely hard to see, so sorry about that. But this is a screenshot of a fork of Surfer. Some of you may be aware of Surfer, the waveform viewer. And this one has additional type information that you absolutely cannot see. Sorry about that. You can check out the slides later. But we created this format in collaboration with Synopsys, and someone else saw it and was like, hey, I want to do type level waveform viewer. So this student, Raffaele Maloney, just kind of reached out and was doing this work, and it's super cool. I don't know much about this work other than that I saw the waveform viewer and I think it's really cool, but this just shows the power of that's why we're here at this meeting. This is the purpose of open source. We didn't know this was gonna happen, and I found out about this 2 weeks ago. So it's pretty exciting. So check out his demo showing type level debugging of Chisel. And then a lightning round of other new features, because I'm running out of time. The caffeine is helping me go fast, though. We have public modules. For any of you who've used Chisel, you're often like, why did you mess with the signal name? Or why did you get rid of ports of my internal module? It's because it's not part of the public API. But now you can mark any module as a public API, and that means you have a defined lowering to Verilog for the ports. That's a helpful feature. We have this module choice feature, which is half working. It's almost fully, it's under development, but it allows you to swap out implementations of modules, really important for verification and for FPGA emulation, right? You need to swap out a different memory model to make sure it maps well to block RAMs, for example. And then boring utils are an old feature, but they support probes and properties. So all of those are treated the exact same way as regular ports. And it also now supports driving signals on the inside. So that's in Chisel 7. So there's not a release that has that yet, but you can actually drive signals cross module. Okay, so what's up next? One thing that is very important for verification and simulation is DPI. That's kind of, if you don't want to be doing everything in system Verilog, but you're verifying Verilog, DPI is kind of like your main escape hatch. And so we are working on first class support for calling DPI from Chisel. People currently kind of do this ad hoc using black boxes. We're trying to make it a properly specified thing. So currently it's just in the proposal stage, but this should be, I suspect this will be done in a couple months. And the hope is that we can generalize this to all external functions. DPI is a particular implementation of an external function, but we're hoping that we can just be more generic with the concept of calling a function from your simulation. One thing I didn't really mention is that a lot of the themes, hopefully the themes of a lot of these new features are verification. That's the biggest problem that I think most people have, and so we're trying really hard to add features that make that easier to do. And DPI is a big one. Another one is direct circuit linking. So this is a work in progress. Currently, you run Chisel, you emit a .fir file, and then that you feed to FIRRTL, which will give you Verilog. That serialization and deserialization is not actually that fast. It's about 10% of the runtime. And so there's some ongoing work to make it to where we can just link the shared library directly into Chisel, and then you don't have to do that. And that might also let us save memory by representing the information more efficiently. Windows support for this is really tricky, though. So if you're a Windows person, I would like to talk to you because I don't know what exactly we should do. Maybe we should just tell people to use WSL. I'm not sure, but that's something I would like to talk with people here about because I don't use Windows for anything except like video games. So I don't know how to develop on it. And then the last thing, this is for my real Chisel people, is Scala 3 support. It's been long requested. Almost every time someone asks a question at work and is like, why is this a little weird? And it is a little weird. I'm like, yeah, sorry, that's fixed in Scala 3. So we're very excited about ultimately making this move, but there's still a few things that have to be done. But I'm pretty excited. The main issue, Scala 2 and 3 are almost entirely source compatible, except for macros, and we make heavy use of macros, so that's where the real problem lies, is in some of our own stuff. It's not really anything about the language. And so that's it. Please get involved. Check out our website, chiseling.org. And yeah, I guess I have a couple minutes for questions.
Nice work, Jack. It's good to see Chisel, going from strength to strength, and appreciate your time and Sci5's time investing in this language because we use it a lot, like at my company, and it's extremely powerful, productive language. I think Olaf had his hand up first.
Yeah, first we have the Surfer developer in the audience, and we'll probably do a lightning talk about that later today.
Oh, excellent.
And my question was, so about the IR, I'm a bit confused because I know you used FIRRTL, you developed FIRRTL for this, and then you talked about MLIR, but also Circuit, I think it's a new thing. So my thought was that Circuit was replacing FIRRTL, or is it more complicated?
So yeah, I should have done a better job defining my terms here. So FIRRTL is an IR spec that is implemented by Circuit, the project. So FIRRTL's not going anywhere. The spec exists. The implementation was just rewritten. The problem was we ran fast and loose and said FIRRTL to mean the spec and FIRRTL to mean the implementation. And the old implementation is deprecated, but the spec is implemented by Circuit. Circuit is a project, a larger project than just FIRRTL. And then FIRRTL is the Circuit binary that implements FIRRTL. And we'll take your FIRRTL in and emit system Verilog. Does that answer your question? And MLIR is the infrastructure that Circuit is built with. Yeah, sorry, a lot of terms, really fast.
Thanks for the talk, Jack. I had a couple of questions about, what do you think about the language evolution plan, and what guarantees do you get version to version, right? So these are major version releases, which implies that they're big breaking changes. So what do you think about the long-term cadence of these developments? How should people think about building both core projects in Chisel and building upon Chisel in terms of compiler extensions, other things you want to add, if you want sort of some amount of stability to do that kind of work. So what are your thoughts there?
Yeah, so we're definitely in an era where we are intentionally moving faster. So for a long time, Chisel 3 was very slow evolving, and so and that has a lot of great things. You can be guaranteed that certain things will work forever or for a very long time at least. The flip side of stability though, is it makes it a lot harder to add features, right? So it's true that these are major versions, but for the most part, we don't break Chisel APIs. We definitely deprecate before we do, but most Chisel, normal Chisel code written against Chisel 3.4 still works against the head of main. It's mainly kind of on the periphery where the major version bump is important because we break Scala binary compatibility, but that only matters if you're publishing libraries. You just need to republish. That is unfortunate, but that is the main thing that causes it to be a major version. As far as actual breaking, for the most part, we don't break Chisel APIs. On the compiler side, though, Circuit is it's very much in the LLVM methodology of if we're bumping the version, we're breaking things, sorry. And that is unfortunate. I hope someday we get to a point where it can be more stable, but I think there's just too many things that they still want to do to have that level of guarantee on the compiler right now.
Hey, Jack, quick question. That Verdi support, so I saw the Chisel source code and then what looked to be an RTL waveform below it. Is that a Chisel sim, or is that annotating generated Verilog to then go from the waves back to the Chisel source code?
It's an annotation of a Verilog simulation, but those waves back to the Chisel source code. Yeah.
I'm finally thinking of moving from Verilog 2005, and the good news about, the only good news about Verilog 2005 is that it hasn't changed since 2005. And so I'm considering Chisel, of course, and kind of one of the questions is there's this whole new world of not high-level hardware description languages, but medium-level hardware description languages. There's MeGen, there's Amaranth, there's Chisel, there's Spinal, there's more that I'm sure that I am missing. And so I'm wondering, so one thing that I'm thinking about that I think you just answered is whatever I move to, I want to not think about again in the same sense that I haven't thought about Verilog since 2005. And the other side of it is I'm thinking about it would be nice to interoperate with all of these other ecosystems. And I'm, it would be nice to, for instance, suck in a LightX world into my Chisel tooling. And so I'm curious what you're thinking about in terms of that interoperability story, and of course about stabilization.
Sure. So as far as interoperability, I mean, there's a lot of levels of interoperability. We do certainly, we link at the Verilog level, right? And part of the thing that, one of the big focuses recently, so I've talked a lot about moving faster, but one of the things that we are doing more than we used to is defining our Verilog API. So at least at that level, we are intentionally trying to make it to where if we say you're emitting certain Verilog, you're going to get that Verilog. And that's really important for interoperability. As far as stability, like I said, the actual Chisel core API hasn't changed in a very long time. So the majority of users, for the majority of things they're doing doesn't change, really. But I will say there's still, we need all these features that we're adding. Sometimes when you add new features, how it interacts with things might require slight tweaks, and we will make those changes as we need to because we want Chisel to be great. I think now it's good. We're trying to make it great, but there's a long way to go.
So that debug transport layer between VCS and Chisel, very cool. Is that spec public? Who's is there a lot of training?
HGLDD is, I don't know if they have a formally written out spec, but it's open standard as part of Circuit. So if you go to the Circuit repo, hopefully you can find something about it.
Perfect, thanks.
Well, because the generated Verilog already has quite a lot of annotation as to which line of Chisel it came from, right? So
yeah, you need a bit richer information than that, a little bit, and that's what's in this format, the HGLDD format.
This will have to be final question, I think.
Can you give some insight on the amount of work that goes into the changes you have to make on the Chisel compiler side and the FIRRTL side when you're adding a new feature? Does that make sense?
Yeah.
There are two systems.
Yeah, I mean, ideally with a well-described language and compiler, most of the work should be in the compiler. So when we spec something out in FIRRTL, usually most of the work is going from FIRRTL to Verilog, and then from the Chisel side, it's more just, the hardest part is trying to make sure the API is good. And that's really difficult, and we get it wrong a lot. But mostly, we just store the data structure and emit FIRRTL. Sometimes it's a little bit harder than that, and there's more of a distance between how Chisel sees the world and how FIRRTL sees the world. So occasionally, there's a lot of Chisel work, but it's mostly in the FIRRTL compiler.
All right, thanks again, Jack. Keep up the good work.
Thank you.
Cheers.